Alright, hey y'all, it's Mr. Kyle Myers Mathematics, and let's just jump into it. We're using the Squeeze Theorem as an, please squeeze my neck, to find the limit of each of the following sequences. And I say, squeeze my neck because I don't like Squeeze Theorem. I'm really not a fan. I really don't like it. It's terrible. It's actually the worst. The worst! So a sub n is equal to n exclamation mark, which I guess is pronounced n! And then you go over into the n power. So n factorial over n to the nth power. And actually, this is kind of, because it's actually fairly simple, I didn't say easy, just said simple. So, I don't know if I've done this in another video or not. Maybe I have, maybe I haven't. But I'm about to teach you guys something really cool on this particular video, and maybe this will be the first time I do this. But when you're taking a limit as it goes to infinity, let's actually start off with this. So I'm going to go, no, what am I doing? White, because I'm using a black board here. Okay. So if you're taking a limit as something goes to infinity, right? A limit as n goes to infinity of some sort of thing. And I'm not going to call it a sub n because I already have an a right here. I'm going to call it z sub n because nobody ever does that. And it equals something, right? So z sub n we can write as a times something, maybe y sub n, because why not, over b x sub n. Now this is looking a little bit complicated, but that's because I'm trying to be as general as I can. I promise I'll make it less complicated as I'm explaining it here. And so basically, if the top is bigger, right? So if y sub n is greater than x sub n, then there's no limit. Then the limit does not exist. So let me do this. Let me do it this way. I erased this. No, chopped off the bottom of the b. Okay, so if y is greater than x, then the limit does not exist. All right. If y is less than x, then the limit is 0. However, if they're the same, meaning like their degrees are the same. So when I'm talking about them being less than or greater than or whatever, I'm not saying like for all values of n, one is greater than the other necessarily. I'm saying that like the degree or the degree equivalence of it is the same. That's kind of how I'm writing this. So then if this happens, then you would get a over b as your limit. Okay, so a couple examples. Actually, you know what? No, let me do this first. So let me show you the hierarchy. Because how do we know which one's bigger, which one's lesser? It depends on the degree or the degree equivalence. And I'll give you a couple example functions here. So sine in, cosine in, the two wavy ones. Speaking of things that are, what's it called? Harmonic? No. Oscillating functions. So oscillation is happening in some way, shape, or form. Or constants. C, constant. So those have a degree of basically 0 because they're just like woo, and that's it, and that's how that goes. Okay, then I'm switching to orange here. So it's like a game of red light, green light, right? Red not going anywhere, right? Red means stop, so degree of 0. Orange, I'm making up extra light colors here. So orange is like you're going really slow. It's like right at the moment where the light is like almost not yellow, but it's not quite red yet. That's orange. And that would be basically a logarithm. They're kind of in their own class. The base doesn't really matter. So, well, I mean, I wouldn't say it doesn't matter, but like, if it's like, 2, 3, 4, 10, E, whatever. And then N, right? So, yeah. So that's like slow, like really, really slow. And then you have, speaking of slow, like either slowing down or speeding up, depending on how close you are to the intersection, right? I mean, if you're really close, but you're not like super close. If you're like really close, you don't really need to change your speed. If you're like kind of close, but it's like you'd have to like really slam on the brakes to stop, then like maybe you tap on the gas a little bit, you know? Um, and then if you're like further away, it's like, all right, I'm not gonna make it if I try to speed up, so I'm gonna slow down and come to a stop. So it just kind of depends. So this is a whole bunch of different functions. This would be no, x, some sort of base. No, because it's in to the power of some sort of thing. Let's call it d for degree. So the degree would literally just be d. That's supposed to be a d. It's a terrible looking d, but it's fine. So into the d power. So if d is like 2, it's a degree 2. If d is 3, then it's a degree 3. So that would be like polynomials, radicals, if d is a fraction, like a half or something. And then we get to, like, if you flip it around. So I guess I wouldn't use d per se. Maybe not e, because e is like the natural number. Let's use f. Nah, that's a function. Why are there not letters for things? Okay, j. And a cursive j. We use a cursive j, because why not? Cursive j to the power of n. Exponential functions. So basically any positive exponential is going to go to infinity eventually, assuming the base is, more than 1. And then the n is like, some sort of positive number. So it'll go to infinity eventually. And it'll go faster than any polynomial. Like a regular exponential growth, will go to infinity. And it'll do it way faster than any polynomial, even if it's like a degree 100. It doesn't matter. It's a totally different class. That's why I'm using different colors here, is because it's like totally different classes of things happening here. Also green, right? Green light. You just put the pedal to the metal, Well, maybe not to the metal. Like, regular street driving, you don't want to be crazy. You get pulled over and they'll ticket you for, what was the ticket for? I don't know. It's called something where you're driving too crazy and they just give you a ticket. Like you can actually get a ticket for accelerating too fast. I don't know if you knew that. So anyways, so exponential, and then after exponential comes factorials, angry numbers. And those are in a totally different class as well, because factorial goes faster generally under normal circumstances than an exponential. It's a different class altogether. So if green means go, blue is like you're in a drag race. And it's like, okay, like any normal street vehicle that's street legal would not be able to beat like a drag racing car. Right? I don't care about what commercial you saw where it was somebody had a Hemi or whatever, and it's like, no, like a drag car will beat a regular car. Now, maybe like a Tesla Plaid or something would give it a run for its money, but those cars are insane. So there's like a totally different class of vehicle here. Okay, and then the only thing that's really faster than that would be compound functions, and one of the most common, at least I think, one of the most common compound functions at that point would be what we have here, n to the n power. And there's variations of this. It could be like n to the n squared or n to the n factorial. Ugh, that would be even faster. Even n to the log n would still be like really fast. When it gets more complicated, you have to be more careful. But generally speaking, this is how it goes. So what's happening here is we have a blue class divided by a purple class. So already, me just looking at this problem, I already was like, oh, yeah, the limit is 0. I already know the limit is 0. That's it, right? Now, as far as actually how you show that and do the work and stuff, it depends on what kind of tools you're allowed to use. On the last problem, I started off using a table because that's pretty much how I always start these off, is by using a table. So I'd probably recommend doing that. And what I would do maybe is you have, so you would go ahead and have your above. Now they're calling it A, which I like to use A for above maybe, but maybe you could do, Space Force, right? Space Force, Semper, what's their slogan? Semper Supra. Semper Supra, always above. I love their slogan. It's so, like, play on words. Okay, so S for Supra, S sub n. This is going to be our above function. Actually, let me move this down. Un momento. So Semper Supra, always above. And then we have our A sub n, the actual function, A for actual, maybe, and then B for below. So you have to come up with two extra functions. We already know one of our functions because it's the one in question. And then we look at in values, right? And they don't say what in value to start at, so we know that the default is 1 unless otherwise stated. So this would be 1 factorial over 1 to the 1, which is literally just 1. And that was a very crooked line. Let's try to make that a little straighter. Okay, that's a little bit better. And then we kind of just go from there. So that would be 2 over 2 squared is 4, so 2 over 4, which is 1/2. You can already see how it's decreasing. 3, that's 3 factorial, which is 6. And then 3 to the third power is 27, so 6 over 27 would simplify to 2/9. 2/9, which is 0.2 repeating. All right, so we went from 1 to 0.5 to 0.2 repeating, already going down by quite a bit. So as we go to infinity, definitely going to go to 0. And then you would select your above and your below functions. And we might be able to just get away with doing the same above and below functions that we did on number 41. So I'm actually going to go ahead and just drag over. I'm actually going to just drag over Desmos again, like I did from the last question. And so here's what we did. Here's Desmos. Da 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 da. Desmos. Okay. I really hope they give me a sponsorship one day. That'd be great. So if you work for Desmos and you want to sponsor Myers Mathematics, I would be happy to promote Desmos. Desmos is amazing, but I currently do not have that, so it is what it is. Okay, so f of x is a sub n, and it is in, which I'm using x's here. Sometimes they are fine with n, and sometimes they're not, so I usually just play it safe and use x's. X to the power of x. Okay, so let's see what that looks like. So red is the thing. Oh, that's interesting. It like starts at 1 and then it goes up actually and then comes back down. Huh. Comes back down and then 1 is 1, 2 is a half, and so on and so on. It's funny because it's not always above it. The green function is not always above it as a totality of the graph, but for specific in values, it is greater than or equal to. Because at 1 and at 2, 1 over x is equal to x factorial over x to the x. But every other value, it's above. So actually, that works. It works just barely, but it works because it doesn't have to be above for every value. It has to be above or equal to for every value, according to Squeeze Theorem. All the nitty-gritty stuff. Part of the technical definition and all that. So actually that works. So at this point, we're basically done, guys. All we would do is we would say that g of x is our above. So our above, which is our s, right? Semper supra. So our above is s sub n, and at 1 it's 1, at 2 it's 2, at 3 it's 1/3, which is 0.3 repeating, which is greater than 0.2 repeating, right? So that works. And then our below is just the negative of that. So it would just be all the negatives, which is definitely below the other one. And it would be fairly easy to prove that. I said this on the last video, but our function, a sub n, is always going to be positive. It's decreasing to 0, so it's always positive. And the other graph is always negative. So it'd be fairly easy to prove, even if you needed to do a lot of proof, even if your professor needs to see a lot of work, all you would need to say really is that a sub n is always positive for all n, and b sub n, the negative 1 over n would be negative for all n, as you know, starting at 1 going to infinity. So that's it, right? Because a positive number is always going to be greater than a negative number, right? So that's all you would really have to say for that. Now, for the other one, that might be a little bit more difficult. If you have trouble with that, or if your teacher slash professor, whoever's, whatever you call them, if they need to see more work for that, just like maybe shoot me a comment in the comments below, and give me some like detail on like what they're looking for, because there's professors need to see a lot of different things. They have their own little whims, you know, of like what they want to see for full credit, and their way is the right way, and blah, 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 and I'm so smart because I have a master's and or a doctorate in mathematics, so you know, whatever, like it is what it is. So yeah, just let me know if they need to see more. But that's basically what you would do, and then you just, you know, you have all your nitty gritty and everything, right? So you would just say, hey, S sub n is greater than or equal to A sub n, greater than or equal to B sub n for all n, and the limit as S sub n and B sub n go to infinity is 0 because they're the harmonic and negative harmonics, or you could say because they're rational functions and their horizontal asymptotes are y equals 0. So therefore, the limit as they go to infinity would be 0. You could say something like that. If they need to see, you know, some evidence, if they need to see some proof, then you could say something along those lines probably. And that would probably be sufficient evidence. I hope, if I was a college professor, which I'm not yet, but you know, maybe one day, then I would hope that they would be fine with just a nice T-chart. Like, oh, hey, this is going to be this, and then this, and then this one is going to be this, and then this, and then this, and this, and this. Like, as long as you have a really good T-chart, I think I would give you like at least most of your credit. I don't know. I'm normally not a super picky professor myself, but anyways, hopefully that answers the question. And like I said, if they're looking for more, just drop me a comment and I can take a look. Just give me as much detail about what the professor is looking for an exact answer. But that's pretty much it. So hopefully that's been helpful. Go check out the 5 math mistakes everyone makes and how to avoid them. That's a free PDF guide. It's on my website, myersmathematics.com. Link in the description below. And I'll catch you all in the next video. Blessings, y'all.